So yesterday we were discussing properties of gases, and we'd actually began with pressure. We said that pressure was force divided by area, but we also have two other variables, temperature and volume, which are variables that are needed to describe gases. A few of the general characteristics of gases: gases have no definite volume, meaning that they can expand or contract based upon the container that they're in. Gases tend to naturally expand, spontaneously expand to fill whatever container they're in. They tend to be highly compressible, but they don't compress themselves, so that requires work to be done to compress them. And all that does is lower the space between the particles, making them more dense. Gases are also, as we said yesterday, this is a poor word choice from PLTW. Gases are less dense than liquids, not lighter. Depends on how much you have to say lighter or heavier, but definitely less dense. And when we're measuring pressure, and this is where we stopped yesterday, when we're measuring pressure, we actually have two types of pressure that we need to consider. The gauge pressure, which is the pressure on a gauge that you can read as the operator of the system. And the gauge, however, really doesn't account for the atmosphere. The atmosphere is always there. There's no way to escape from it. And because of that, the gauge pressure needs to be adjusted sometime to give an absolute pressure. The absolute pressure is the atmospheric pressure plus the gauge pressure. So from an equation standpoint, gauge pressure plus atmospheric pressure yields absolute pressure. Now this could even be, for instance, when you're looking at a tire, and you want to check the air pressure on a tire, and you put maybe it's a flat tire, and you put the gauge to the tire, put it on the valve stem of the tire, and it says that there's zero pressure. That's not actually true. It's actually zero above atmospheric pressure, meaning that the air inside of a flat tire is the same pressure as the air outside the flat tire, which happens to be atmospheric pressure. So if we pump up a car tire to 32 pounds per square inch, then what we would actually say is that the gauge pressure that we see is 32, but it's really 32 plus whatever the atmospheric pressure is, which, on an average day is about 14.7 pounds per square inch. All right, so pressure is measured in both pounds per square inch, or also called PSI. And standard atmospheric pressure in that unit is 14.7 pounds per square inch. I also gave you some variation on those pressure units yesterday. There are lots of pressure units, and I gave you the standard pressure in each of those. So if a gauge reads 120 psi, what's the absolute pressure? It's going to be that 120 plus the atmospheric pressure here to give 134.7 pounds per square inch. So temperature is also something that needs to be discussed. We also have an absolute temperature, and 0 degrees Fahrenheit. LTW is looking at the Fahrenheit scale here. We could also look at the Celsius scale in the same way. 0 Celsius is also not a true 0, but 0 Fahrenheit does not represent a true 0. Absolute 0 is at negative 460 degrees Fahrenheit. So this will be the lowest temperature, the 0 temperature. Absolute temperature is measured in degrees Rankine. So this is represented by the letter R. This is used in engineering in the United States quite a bit. If we were talking about the Celsius scale, the absolute temperature in Celsius is measured in Kelvin. So Rankine is to Fahrenheit as Kelvin is to Celsius. So to get the Rankine temperature, Rankine is going to equal the degrees Fahrenheit plus 460 plus 460 Fahrenheit. Actually, 460 Rankine. So Fahrenheit plus 460 gives Rankine. So if the temperature of the air of a system is 65 degrees Fahrenheit, what's the absolute temperature? All we have to do is add 460 to that, so 65 degrees Fahrenheit plus 460 is going to be equal to 525 Rankine. So I'll say more about this when I return tomorrow, but just for right now, add 460 and you will get the Rankine. In Pascal's law, we mentioned yesterday in a form, but it's an important form in terms of the engineering of pneumatic and hydraulic systems. So Pascal's law states that pressure exerted by a confined fluid acts undiminished equally in all directions. You may remember the container with the 1 square inch stopper. If you press on it, then it expands out to the entire 20 square inches of inside space in the container. And it's just a multiplication of the two to get the total pressure. So pressure is the force per unit area exerted by a fluid against a surface. It's actually the molecules of the fluid that collide with the surface or with the walls of the container that lead to the phenomenon that we know of and measure as pressure. So P is equal to F over A. And our pressure units are going to be the product, or excuse me, the quotient of pounds and square inches, so pounds per square inch. So an example using Pascal's law is how much pressure can be produced with a 3-inch diameter cylinder and 60 pounds worth of force. Okay? So here's our cylinder. We've got a force applied out here to the end of the piston. And to the rod, I guess you would call them the piston, and the piston is going to be extended down into the cylinder. Okay, so 3-inch diameter, 60 pounds worth of force. Okay, so what we have given to us, and we're looking for how much pressure. So diameter is 3 inches, force is 60 pounds. Pressure we need to know, and to solve for that pressure, we also need to know the area of the piston surface. Okay, so the formula for that area is pi times r squared, and that's going to, if you substitute and solve, we have an r, since diameter is 3 inches, cut that in half to get the radius, and that would be 1.50. We're going to square that, multiply by pi, and we get 7.07, and they are noting down here that this number, just for this slide, is rounded, but if you're solving the problem in your calculator, you shouldn't round. You should use the value on your calculator at this point to substitute into the next problem. That avoids over rounding. So then, once we have the area, which is the diameter of this piston surface, so the pressure is equal to the force that's exerted, which was the 60 pounds, divided by the area, which is the 7.07 out to more decimal places area. So that's 60 pounds divided by 7.07 square inches, and that comes to a pressure of 8.49 pounds per square inch. Now, anyone that works with gases needs to know something about what are called the perfect gas laws, or sometimes the ideal gas laws. These are simplified, actually, that's the reason for the term perfect, simplified equations that represent the behavior of gases in pneumatic systems. They do hold within certain temperature ranges. If you get to temperature or pressure extremes, they tend to break down and you have to go to something known as real gas laws instead of perfect. So the three that PLTW needs you to know about are Boyle's law, Charles' law, and Gay-Lussac's law. Okay, Boyle's law is probably one of the oldest equations in modern physics and chemistry. Dates back to the 1600s with the English physicist Robert Boyle. Jacques Charles was a French physicist studying gases also, and Joseph Gay-Lussac was also a Frenchman, and actually was the first person to fly in a hot air balloon. And it's actually a famous painting, which I can't think of the name of right now, that shows his ascent in the balloon over a field in France. That also led to the first Air Force, by the way, which was using hot air balloons to survey battlefields in the probably 1700s. Let's look at Boyle's law first. Boyle's law describes the volume of a gas at constant temperature and how it varies when pressure is exerted on it. So this is a relationship between pressure and volume, as you can see from the graph over here. So this says the volume of a gas at constant temperature varies inversely with the pressure exerted on it, meaning that as you increase the pressure now, and again, as you increase the pressure, the volume of the gas is going to decrease. So as you push on it, the particles inside get closer together. One thing that we do have to say with this is that the temperature during this time is, you need to hold that constant. So we only have two variables that are working, and that would be volume and pressure, constant temperature, and also the amount of gas inside is also considered to be a constant during that, although you will not have to do any equations with amounts of gas, which gets into the mole concept. And so the equation, this is known as the proportional form of Boyle's law, is that pressure times volume equals pressure times volume. Ones are the initial conditions, so a gas that has a certain pressure and a certain volume, if you change the pressure, you can predict the volume. This type of problem is known as a volume or pressure correction problem, meaning that I have a pressure and volume under certain conditions. I'm going to change one of these two variables from the original and predict what's going to happen to the other variable. Okay, and back to this for just a moment. Symbol V is for volume. That's the space occupied by the gas, and that is in cubic inches or milliliters or liters or gallons or whatever volume unit you choose to use. It doesn't matter what volume unit is here, but they do need to be the same. So if we have two pressure units given, they need to be in the same unit. If they have two volumes given, they need to be in the same unit. Okay, so an example with Boyle's law. We've got a cylinder that's filled with 40 cubic inches of air at 60 psi. The cylinder is then compressed to 10 cubic inches, so the volume is compressed to 1/4 of what it originally was, which was 40, plus the resulting absolute pressure. Okay, so there's the graphic of what's happening. And what we've got, first of all, we've got the initial pressure is 60 pounds per square inch. Second pressure is what we're solving for. We've got an initial volume of 40 and a final volume of 10 cubic inches. First thing that we need to do is convert the pressure from a gauge pressure to an absolute pressure, because we are actually asked for absolute. You should consider pressures given in problems to be gauge pressures unless you're told otherwise in this course. So pressure 1, the initial pressure, is 60 pounds per square inch plus atmospheric pressure. So this is gauge pressure plus atmospheric pressure gives the absolute pressure to begin with. Okay, so 74.7 is our initial pressure. So we then take the formula P1V1 equals P2V2, and we substitute 74.7 for P1. 40 cubic inches is the volume of the gas under that pressure. We then set that equal to the second pressure multiplied by 10 cubic inches, where the volume has been decreased to 1/4 of its original volume. Then solve for P2 by dividing both sides by 10, as you can see here. And that is going to give us a pressure. So in the numerator, this is the 74.7 times 40. That gives 2,988 inch-pounds, because we have a square inch here and a cubic inch here. So that's going to be that's going to leave inch on top. We're then dividing by 10 cubic inches, and that's going to give us, see if I can, there we are. That's going to give us a pressure of 300, or 3 times 10 to the second, pounds per square inch. Interestingly enough, when you look at this, the value that's on top, the pressure times volume, gives inch pounds. If you think about that, that is a distance multiplied by a force. That's not minus, that's a multiplication. That should be just a dot. And that actually is work, because when the value that we have up here is the work done on the gas as it's being compressed. So there's 2,988 pound inches or inch pounds worth of work done, and then we divide that by 10 square inches. And our final pressure in pounds per square inch isn't absolute, because we started with our absolute pressure at the beginning. You should also be able to solve this with the 60 pounds and solve for the gauge pressure, P2, and then convert at the end from gauge pressure to absolute pressure. Should work either way. Next we have Charles' law. Charles' law is the relationship between volume and temperature. And as you can see here, as we increase the temperature of a gas while holding the pressure constant, the volume is going to increase. Okay, but the pressure over here, notice that the pressure on the gauge is holding constant, but the temperature is increasing or decreasing. As it increases, it gets bigger. As it decreases, it contracts. So the volume of a gas increases or decreases as the temperature increases or decreases, provided the amount of gas and pressure remain constant. Again, our mass or number of moles or number of particles of gas in the cylinder is holding constant. Okay. Our proportional form of this law is V1 over T1 equals V2 over T2, and it is important to note that for this to be a direct proportion, which is what this is actually showing, this has to go through zero. At zero temperature, volume would be zero. For that to happen, our temperature has to be on an absolute scale, either Rankine or Kelvin. So as an example, an expandable container is filled with 28 cubic inches of air and sitting in ice water that is 32 degrees Fahrenheit. The container is removed from the icy water and is heated to 200 degrees Fahrenheit. What's the resulting volume? Okay, so we've got a cold gas that's going to be heated, and we want to see what's going to happen to its volume. Okay. So our initial volume, 28 cubic inches of air. Our final volume is what we're looking for. Our initial temperatures in degrees Fahrenheit are 32, final is 200. We have to convert the temperature to the absolute scale. So to do that, we add 460. So T1 is 32, this 32 plus 460 to give an initial 492 Rankine. And then temperature 2, Fahrenheit plus 460, or 200 plus 460 to give 660 Rankine. It is important to use the proper temperature scale here. We then substitute into our equation for Charles' law. So we have 28 cubic inches, the initial volume, the initial temperature, 492 Rankine. We're looking for the second volume, and we're solving for when we have a final temperature of 660 Rankine. We're going to cross multiply and divide. That gives 660 times 28 is 18,480 cubic inches. And that would be Rankine times cubic inches. That's what we've got up top here. And then divide by 492, which is Rankine, so Rankines cancel. And it leaves us with the final volume of 38 cubic inches. So we're starting with 28 cubic inches. We increase the temperature, so the volume should increase, and that is what we have. All right, with Gay-Lussac's law, Gay-Lussac's law, the absolute pressure of a gas increases or decreases as the temperature increases or decreases, provided the amount of gas and the volume remain constant. A good example of this is with a basketball that's left out overnight on a cold night. When you go out, maybe it was in the afternoon the day before, you could dribble it very easily because the pressure was high. The pressure makes it bouncy. And you can dribble it if it's bouncy, of course. And then you go out the next morning and it's in the 30s outside, And the end result is that when you try to dribble it, it doesn't bounce very well. It might not even bounce off the ground, depending on what the pressure was. The lower the temperature, the less it's going to bounce. The reason for that is that the gas inside is not exerting lots of force from the inside of the ball, so the end result is that it's just not springy. Okay, so our equation for this is P1 over T1 equals P2 over T2. The initial pressure divided by the initial temperature is proportional to the final pressure divided by the final temperature. Note that again, temperatures have to be on the absolute scale, so Rankine or Kelvin, and P1 and P2 refer to absolute pressure. Absolute pressure meaning not gauge pressure. So in the first example, we have a 300 cubic inch sealed air tank sitting outside. In the morning, the temperature inside the tank is 62 degrees Fahrenheit, and the pressure gauge reads 120 pounds per square inch. By the afternoon, the temperature inside the tank is expected to be close to 90 degrees Fahrenheit. What's the absolute pressure at that point? So in other words, we start out with a cool morning, and by the afternoon, it builds into the 90s. Okay, so we've got an initial volume of 300 cubic inches, an initial temperature of 62 degrees Fahrenheit, 120 pounds per square inch for the initial pressure, and then we've got a temperature of 90 degrees Fahrenheit. So T1, T2, this is a volume. The volume is not going, we're expecting the volume to stay the same if we're dealing with Gay-Lussac's law. So what would be changing is the pressure, P2. Okay, so the volume, in other words, isn't used. We're going to convert P to absolute pressure. So our initial pressure of 120 pounds per square inch plus 14.7. So gauge pressure plus atmospheric pressure gives 134.7 pounds per square inch. We then convert the temperatures, both of them, to absolute by adding 460. So here are our absolute temperatures out here, 522 and 550. So the temperature is going to go up. And then we have the formula, P1 over T1 equals P2 over T2. And we substitute our values. P1, 134.7 pounds per square inch here. That's the that's the absolute pressure, over 522, the initial temperature in Rankine, equals P2 over 550, the final temperature in Rankine, and then we just solve the math. 550 times 134.7 is 74,085 pounds per square inch times Rankine. Divide by 522, Rankines cancel, and we end up with a P2 of 140 pounds per square inch. Notice again that volume was not used. In Gay-Lussac's law, volume and mass of gas are actually constant. Okay, so the final pressure is 141.9. Back for a moment. So final pressure 140 pounds per square inch. And then if the absolute pressure is 141.9, so this is the unrounded value. If the absolute pressure is 141.9 pounds per square inch, what is the pressure reading at the gauge? So to get that, we're going to have to subtract atmospheric pressure. So we're looking at the gauge pressure now. So that would be absolute pressure that we found here minus the gauge pressure to give 127.2 should be the reading on the gauge, which is approximately, rounded to 2 sig figs, 130 pounds per square inch. That is where we will stop this presentation. From this point, you should be working on the problems on pneumatic practice problems on your agenda at Northside Science.